Hello everyone. In this particular class, we will be covering elliptic curve cryptography. It is another kind of asymmetric cryptography, which is based on elliptic curves. Um, the reason we are studying this is that it provides equal security in comparison to RSA. Like it provides equal security with lower key size in comparison to RSA algorithm. So if you recall in RSA, we were choosing two big prime numbers and then we were calculating n, then we were calculating phi n, then we were calculating e and d values. So once again, these p and q values that we were taking were very large prime numbers. So if we are having a key size of 512 bits in RSA algorithm, you will be using 112 bits in elliptic curve, which means that it is less computationally expensive in comparison to RSA algorithm, and thus provide, I would say, equal security and less computationally expensive. And that's the reason people started um, like using this elliptic curve. So cryptography, elliptic curve cryptography is based on mathematical formula, um, which is y square equals to x to the power of 3 plus ax plus b, where these values, which is a and b, can be changed. So a and b values. So let's suppose if I change this value, substitute this value as 1 and b value as -1. So y square becomes x cube plus x minus 1. So it will have one kind of curve. If I change it to some other value, y square, x cube, a value as 0, b value as 7, this will make another kind of curve and so on. So you can change these values in order to get these elliptic curves. But what is this? What is the beauty of studying this elliptic curve? Like, what is the important properties of elliptic curve? So, the important property of elliptic curve is that it is symmetric along the x-axis. So, whatever you see above x-axis, you will see the similar kind of image in the below x-axis. The other thing that you see in elliptic curve is that if you draw a line on this curve, this line on this curve, it will always touch 3 points on the curve. So here in this case is this one, the other one is over here, and the third one is over here. So you can see that it is touching three, a maximum of three points. It can achieve two, it can touch one. It depends upon the way you are drawing the curve, but it will never touch more than 3 points. That's another important property of this elliptic curve. So if I'll draw certain, if you will see certain graphs that has, when we substitute this value. So if I substitute the value of A as 0 and B as -1, you will get a curve something like this, which is the first curve. When you substitute the value of A as 0 and B as 1, then you will get a curve like this. All of them is very symmetric. Now it is -3 and +3, you will get a curve like this. When you substitute this as -4 and B value as 0, you will get curve like this, and so on. So you can achieve many curves, and all of them are symmetric on x-axis, and it can touch a maximum of 3 points. So how can this be visualized, and how can we utilize this in solving cryptography-based algorithm, which is asymmetric key cryptography? So imagine you are playing a game of billiards, or on a pool table, you are playing this billiards where you have to use your stick and you have to pull all these balls to turn around here and there. So imagine you have a ball that you are aiming, and when you point towards that ball, what it does is that it achieves some kind of path, and that path is based on where do you start. So when you start your ball from here, it will it will start going in one direction, and then the ball will hit the curve, and then it will go in bottom direction, and so on. I had this animation which is over here. If you will see that it comes over here, then this, and goes in this direction, and so on. So when you are playing this game, the public key you will take is the starting point and the ending point. So let's imagine that you want to start from A and you want to reach to the position E. So that becomes public, and the private key over here is the number of hops that you took in order to get to the position of E. That becomes private, and you do not know from A to E. You can have n number of directions to come and achieve that particular position. So that's what elliptic curve cryptography in general says, that you make these A and E as the public key, and private key is the number of hops. So when we call this billiards moves on 2 points, we do a dot product. So A dot B, which is A dot B, will achieve a value which is minus C. When we draw a line from A to B, it intersects a point called minus B, which is hitting to the other side, and that's what it basically says. But let's try to understand, before we go to the mathematical derivation, I also wanted to explain you a trapdoor function. So trapdoor function is a function which says that it is easy to compute from in one direction, but difficult to compute back in the opposite direction. So let's suppose if we have a mapping of x and y with each other, where y is a function of x, and given the value of x, it is very easy to get the value of y because you know the corresponding function. So if you recall, in homomorphic encryption, we were calculating f of x, where x value was changed. We were using that truth table that we created. So we were able to get the value of y if f of x is given, but not in the opposite direction. If y is given, how would you calculate x? That becomes difficult, and that's what the trapdoor function says. It is hard to get the value in opposite direction when you know some value. So that's what trapdoor function says, and it is very much applicable in this elliptic curve, that given two values, you can easily compute in one direction. But let's try to understand this, and how do we achieve this kind. Let me open my whiteboard. Okay. So let's suppose I am drawing an elliptic curve. So let's suppose I have this x, y. Sorry, I'm drawing it on tablet, so my drawing could be bad. But anyways, you have this curve which is coming in this direction. And another thing is that this curve is like it reaches to infinity, but for representation purpose, I'm just saying that it is bounded till n value. So it's all the curve which is you are able to see before the value of n. So when I draw any line, so let's suppose I draw a line over here. I'll try to draw a line so that it touches 3 point, but if it doesn't, just bear with me. So let's say this is, let's suppose this is touching over here. This is another one. This is another one. So this is P, this is Q, and this is R. Okay, so it is touching 3 points, presuming that R is within this. So the EP is an elliptic curve on the values of A and B, because we change these values A and B in order to get that. So consider equation. Let's Q is equals to K times P, which means that Q is achieved when we multiply K times P, we will be able to get the Q value. So here Q and P are some points on the curve where K is less than N, because it's within this axis. So if K and P are given, what does this trapdoor function says? That if K and P are given, it is very easy to compute the value of Q. But if we know Q and P, it is very hard to find the value of K, right? You are, uh, you know the starting point and the ending point, but you do not know how many times it takes to achieve the number of hops. And that's what it is called as the discrete logarithmic problem for elliptic curve. A to B is easy, which in this case is when Q and P, K and P value are given, then it is easy to compute the value of Q. But when Q and P are given, it is hard to compute the value of K. That's what the trapdoor function says. And now try to understand this elliptic curve in terms of some mathematical formulation. So here, as I said, imagine that you have drawn a graph in such a way that EP is the curve on A and B, where the parameters A and B are changed. P is the prime number or an integer in the form of 2 raised to the power of m. Okay. Now let's imagine that G is some point on the curve whose order is large value of n, like where G value is greater. So let's suppose that, as I said, it is bounded within n. I'm saying that let us imagine that G is some point on the curve whose order is large value of n, which is greater than this n value. So the key exchange value that happens over here is, let's suppose A and B wants to, Alice and Bob wants to communicate with each other. So Alice will select a value NA in such a way that NA is less than N. And that is the private key for Alice. Okay. So NA, which is the private key and which is the value which is lower than the value of N. That becomes the private key for Alice. Similarly, for Bob, the so Alice is doing all this computation. This is the private key, and it will also create a public key, which is NA times G, which is the public key. So this is public key of A, and this is the private key. This is private key. So Alice computes these two values, and then it keeps the private key with itself, and it transmits the public key, which is NA times G, which is just the PA value it sends to Bob. And the key exchange protocol, which happens over here, is that Bob also does a similar kind of computation. It takes a value of NB, which is lower than N, and it keeps this as its private key. And it also computes the value of NB times G, which is once again that G value, as I said, was common to both of them. And this value becomes the public key for Bob, and this is for Bob. So this NB times G is the public key for Bob. Now the calculation of the secret key happens in such a way that by user A is when it receives this value, which is PB, because this is public. So this will be transmitted back. So let me change over here. This gets transmitted to Bob, and this gets transmitted to Bob transmits P of B, and Alice transmits P of A. So this value, the calculation of the secret key happens is that since this is common to Alice knows this, it will take NA times PB, which was sent from Bob, and this becomes the secret key, which is K over here. And in this case, the key K is NB because Bob has this private key, which is NB times P of A, which was sent. And if we'll substitute this value, P of B is NB times NA times NB times G. And here NB times PA value is NA times G. So in the end, we are getting the same secret key. So even though they kept, which is very similar to our Diffie-Hellman algorithm, that that even though that you are taking those two secret or private key, and the end you are able to get the final value in this case. And where G is the public key, NA and B are the private key which is utilized. So this happens with respect to key exchange. How does the encryption happen? So this was just the key exchange. Now let's get back to the key exchange protocol. So let me open the whiteboard once again. Okay. So going back, and if you recall, that was Alice, Bob. Alice chose NA, this chose NB. The common thing that was shared was G between them. And in the end, it calculated NB times G, and this calculated NA times, sorry, this was NB times G times NA. And here also we were getting NA times NB times G. But what it was calculating was NA times G. So this was doing NA times G, and it was doing NB times G. So for the encryption algorithm, what they do is, so ECC encryption is something like this. Let us suppose that you have to send a message M. First, you encode this message M in such a way that this M lies in that curve. So that curve, if you recall, was something like this. We take, so this is XY, and this was N. What I'm saying is, you want a message M, you encode this message M in such a way that it is a point on the curve, on this elliptic curve. So let this point that you achieve is P of M. Okay. When you make this message into a point, it is P of M. For encryption, what you do is you choose a random positive integer K for encryption. And the ciphertext is K times of G, because G is common. So that is the first one. And the second one is PM, which is the message of that point, plus K times PB, which is the public key. So here in this case, the public key was, this was PA, and this was PB. So when you are encrypting this message, what you do is you take the public key, which is NB times, because Bob is doing this particular setup, Bob will be sending this PB value, and Alice, on receiving this, Alice wants to send the message. It will take some random integer K value. So K times G it will do. And it will take this point in this message, which was P of M, plus K times PB. PB is the public key which was given to Bob. So now Alice will send this message to Bob, which is ciphertext, which is this value. Okay, so this is the encryption. For decryption, what happens is, so this is encryption. Now let's talk about decryption algorithm. In decryption, what we do is that we multiply the first point. So it sends these 2 points, right? These 2 values. It multiplies the first point with the receiver's secret key, which in this case is N of B. So it will take the first point, K times G, multiply it with n of b, which is private for Bob. So n of b. And then it subtract it from the first, from the second point, which in this case is this. So Pm plus Kp minus Kg times n of b. And we know that P of B is NB times G. So if I'll substitute this, so Pm plus NB times G minus Kg times N of B. So you can see I can subtract these values, and at the end we will get P of M, and which was a point for that particular message. So we are able to achieve the encryption and decryption provided we had this particular secret key in such a particular manner. So as I said, in ECC algorithm, you can achieve better equal security in comparison to RSA. So ECC and RSA, what you get in 512 bits, you can have it in 112. If you have 1024 in RSA, it is just 160 bits. 2048 in RSA, it will be just 224 bits. So why to use such a complex system when you are able to achieve equal security? Now let me give you the example that I can ask in the exam. So let me create another whiteboard. So as I said, an example for this is, as I said, ECC algorithm is specifically based on some curve. So let's suppose my curve is x to the power of 3 plus 2x plus 3, where a value is 2 and b value is 3. So as I said, this is an elliptic curve on a value a comma b. And this I'm doing a modulus operation, which is p, which in this case is 13. So this is E of 13 times A and G, which is 2 comma 3. So I am drawing an elliptic curve, EP, which is E13, 2 comma 3. So next what we do is we calculate generator G. So and a quick thing before I move towards what exactly is generator G. A generator in the earlier examples that I had discussed is generally a value that if you multiply with G, then 1 times G, 2 times G, 3 times G, 4 times G, you are able to get all the values between 0 to P minus 1. We know that generator G, if P is belongs to a cyclic group, let's suppose 17, and if I take the generator 2, which is co-prime to the value P, which in this case is 17, you are able to get all the values. So 2 times 1 modulus 17, 2 times 2 modulus 17, and so on. So here in this case for elliptic curve, what is generator G? It is generally a point where you take a point G in such a way that if you will multiply 1 times G, 2 times G, 3 times G, you are able to get all the points on the curve. And that's what the generator G in this case is. So let's suppose I have a value which is, I have a curve which is x to the power of 3 plus 7, where a value is 0 and b value is 7. And I have modulus 17 in this case. So let's suppose I take a value G in this case, which is, let's suppose, I think they had given this value, but let's suppose this is some value over here, 5, 9. Okay, 5, 9 is the generator. So what it does, it does 1 times 5 comma 9, 2 times 5 comma 9, 3 times 5 comma 9, and so on. And you would see that in the end, you are able to get all these points, whether you do 1 times, 2 times, 4 times, and so on. And you can check, you can cross verify, and I'll give you one example as well, that when we are taking this generator G, and if we multiply it, you are able to generate all the points at the end. So here in this case, the generator, this G would also be given to you. You do not have to compute the value. So let's suppose the generator for this elliptic curve, which is E13, 2 comma 3 is 7 comma 3. So Alice and Bob wants to communicate with each other. And in this case, we are calculating the value of the secret key in this case at the end. And N value is 18, which means that um, it's an elliptic curve under finite field. So what does Bob and Alice does? So Bob, N of B value is 7. That is private to Bob, and N of A is 5 value, which is private to Alice. So if you recall, P of B was NB times G. So NB is 7 times our generator, which is 7 comma 3. And this is done on modulus operation, which is 13. So 7 times 7 is 49. 7 times 3 is 21 mod 13. And that you get is 10 comma 8. Okay, 49 modulus 13 and 21 modulus 13. So P of B becomes 10 comma 8. Alice does similar kind of computation, which is P of A, which is NA times G. So NA has taken 5, G is 7 comma 3 under modulus operation, which is 13. So if I do 7 times 5, 35, 5 times 3, 15, mod 13, you will get the value 9 comma 2. So now this gets transmitted. So Alice transmits 9 comma 2 and Bob transmits 10 comma 8. And what is common between them is the G value, which is 7 comma 3. So Bob, on receiving 9 comma 2, which is P of A, what it does, it multiplies it with the private key of itself, which is 7. So what it will do 7 times Bob, this is Bob, 7 times 9 comma 2 mod 13. So you will do 7 times 9, 63, 7 times 2, 14, mod 13, you will get the value 11 comma 1. And similarly, Alice receives 10 comma 8. It will multiply it with the private key of itself, which is 5 times 10 comma 8 mod 13. So this becomes 50, 8 times 5, which is 40 mod 13. And if you will do this, it will 11, 1. So at the end, we are able to receive the secret key, which is 11, comma 1. So here, if you see that we have done a key exchange algorithm, and the secret key is achieved using this elliptic curve where P was taken, where A and B value was taken, and you can exclude this. You can exclude, this is not given to you, but generally this N of 18 basically says that how many times it takes to get all these values, but you can exclude it right now. Alice and Bob wants to communicate. They will take some secret key, which is N of B and N of A, and then it does all of these computation. At the end, we get the secret key. So you can expect a question like this in the exam, where all of these value P would be given, A and B would be given, and generator would be given, and also some private key, and something like this you can expect in the exam. Or I can just ask you, what is the final value at the end? What is the secret key you are achieving at the end? So that's all. We have covered all the asymmetric algorithm. And I think if I have time, I will also do an message authentication code and hash function. Okay. Thank you, everyone.